to this sweet bearded man. Oh, no beard. Sorry. This one doesn't have a beard. This is weird. Yeah, he does have kind of a clean cut guy. Which is like, he's really ahead of his time there. So, he came up with Lenz's law in about 1833, and when we talk about inductance, it has a symbol L. Guess whose name starts with an L? It's Lenz, so that's where that comes from. Fun little history, okay? So Lenz's law is sort of this effect that we did in the lab. So now that you're super confused by that, we'll talk about what we were actually dealing with. So if you put as we remember, if you put a bar magnet through a loop one way, you get a current in one direction. When you pull it out, you should get a small current in the other direction. Anytime the magnet's not moving, do you get a current? No, okay? So moving a magnet through a loop of wire induces the current. And Lenz's law is sort of this subset of Faraday's law, which we'll talk about a little bit more in a minute, which gives you the direction that current's going to go, okay? And so the rule is a changing magnetic flux through a loop of wire induces a current in the wire in the direction which will oppose the changing magnetic flux. And that sounds really complicated, but let's sort of work that out with a few examples, okay?
Let's imagine that you have a loop of wire in a magnetic field, and we're going to duplicate this thing. So here's a magnetic field going out of the page up top, and a magnetic field going into the page down at the bottom, okay? And we're going to duplicate this a few times so we can do this in a few different versions. Okay, so here we have 3 different situations where we're coming out of the page, and 3 different situations where we're going to have our magnetic field going into the page. Up here, let's do be steady, meaning this is a constant magnetic field, okay? So when we think about that, and we think about the magnetic flux, what's involved in the magnetic flux? Well, that's going to be the magnetic field is a dot product of the area, okay? So the magnetic field is constant. Is the area changing? Now the area is also constant. So when you get BA, this is going to be equal to a constant. In order to have an induced current, you have to take the derivative of this flux. If it's a constant, that means this derivative is 0. Now, that's more of a Faraday's law, which we'll get to in the next part of this chapter, but Lenz's law tells us once we decide if we have an induced current, which way is the induced current. And in this case, we're going to say, well, we're not going to have an induced current because our flux is constant. Okay, so that means there's no current through this loop. So this thing has no current. Down here, it doesn't matter if it's into the page or out of the page. So when we have it into the page, it also has no current. And this is because there is no change in flux. Okay, so the flux, meaning the magnetic field or the area, has to change in time. Since both of these are constant, we don't have a change in flux over time, and we have no current. So let's try the next situation. Let's say our magnetic field is increasing. Same here. So let's start with this situation where we have a magnetic field out of the page, and we know that it's getting bigger. Okay? So now when we look at flux, we know that the magnetic field is changing with time, even though the area isn't. And Lenz's law tells us the direction we would expect the induced current to go. And in order to really understand the induced current, let's talk about the induced field. So if our field we start with, this B, is pointing out of the page and increasing, that means in order to counter that, to try to get back to the original field, we want to subtract off with our induced field. So this would be B induced. And then we just use the right-hand rule from what we would assume is our induced magnetic field in order to get our current. And so we point our thumb into the page and curl your fingers around the wire, okay? Remember, this is our wire. And so we're going to find ourselves going in a clockwise direction. So our current, our induced current, is clockwise. Okay? For this one. Now we'll get pretty much the opposite thing down here, because if we have all of this magnetic field that we start with going into the page, that means our induced magnetic field's coming out of the page because we see that our magnetic field is increasing. So we always want to try to get back to our original field. So if we started with a magnetic field of 5 and it's going to 6, 7, 8, 9, then you're going to want this counter field that comes out of the page, right? So it's going to point out of the page. And if we have a magnetic field induced that points out of the page using right-hand rule, we point our thumb out of the page and we curl our fingers with our right hand, and that will be counterclockwise. Okay, so your current is counterclockwise. Okay? Let's go through the same logic over here, but let's assume that these guys, B is decreasing with time. Okay, so now, because we have this magnetic field that points out of the page, but it's falling, it's dropping. So let's say it starts at 5 and it's going to 4 Teslas, 3 Teslas, 2 Teslas over time. In order to stay the same, we have to sort of boost what we had before by having more magnetic field, so our B induced, also coming out of the page. So it's counteracting the decrease by adding more magnetic field in the same direction. Then to find the current, we use the right-hand rule. So we point our thumb out of the page, and that means the current goes this way. So our induced current is going to be counterclockwise. Okay? Down here, if we start with a magnetic field pointing into the page, then we have to also induce a magnetic field going into the page, which means that we're going to end up with a clockwise current. All right, I hope that helps.
Then we try this out, see if we know what's going on now. So it's either clockwise or counterclockwise. There is a current, so decide between A and B. Yes, so this is going to be clockwise. So look, here's your initial magnetic field. Which way does it point? Up. Okay? Is it increasing or decreasing the flux?
Increasing.
Increasing, because as you move the magnet closer, the field gets bigger. Okay? So we have an increasing magnetic field that's up. That means to oppose that change, your induced field should point which way? Down. Which means you have a clockwise current that goes with your downward field. Okay? Alright, did you?
No.
Okay. So, this is my quicker question. So, here we have a switch that's been closed for a long time. So we have a loop where the current is going like this. Okay? And how do we know the current's going like that? The battery, right? The current starts here at the battery and it goes around the loop like this. So we have an initial, also. Well, but where did the arrows go? Okay, so which way does the magnetic field point? The initial one.
Should be up there.
Up. Okay. So right now we have a constant magnetic field that points up. So in this loop, it also points up. Okay. So constant magnetic field that points up. And the switch has been closed for a long time. So while the switch is closed, do we have any current in this loop?
No.
No. Okay. When we open the switch, are we going to have current in that loop? Yes. Okay. Which way?
The other way.
Or, no, the same one.
The same way. Why?
Because that's when you flip the switch is open.
So is this, when this switch is open, what happens to this magnetic field? Does it get bigger or smaller?
Smaller.
Smaller, because it becomes 0. Okay? So once this current stops, we go from a magnetic field that points up to 0 magnetic field. That is a change in the magnetic flux over time. Okay? magnetic field goes from something to 0. And so the current in this loop is going to try to maintain that same magnetic field. It's opposing the change. The change is the magnetic field's going away. So this one's going to create a magnetic field that matches the initial magnetic field. Okay? So this is going to generate an induced magnetic field that points up, which gives you a current that goes in the counterclockwise direction. Okay? So induced current will be counterclockwise. All right? It's a little bit more tricky when you have coils because you have to be conscious of the way the coil's winding. So I want you guys to try this one out. And we're just looking for the current in this part of the wire. Okay? So is it going right to left or left to right?
So we're going to be using a lot of right-hand rule here. So we're reading the question and we see that the switch has been closed for a long time. That's a pretty big indicator of what we need to do. We want to know what will be the direction flowing in coil 2, so that's over here, when the switch is open. So if this has been closed a long time, that means that we start out with this situation. And so that means we start out with a magnetic field going through this coil. So we start out with B, and then later, when this is open, we end up with a magnetic field of 0. So once again, we have a decreasing magnetic field. Okay, but what we're concerned about here is direction. So when this is closed, that means we can use the right-hand rule to curl our fingers with this. Okay, so when we curl our fingers, that's going to leave our thumb pointing to the left. So that means the magnetic field lines are going to look like this. And because we have this iron core, which is what we assume this is, but it looks like metal, the magnetic field over here is going to be the same as the magnetic field over here. So we start with this B, okay, that points to the left, and then we go to 0. So we have a decrease in the magnetic field. Well, that means our induced magnetic field is going to point in the same direction, which means we use this B for our thumb to curl our fingers in the direction we think that the current's going to go. So in order to get that magnetic field still to the left, we need our fingers to curl like this, which means using right-hand rule, we're going to get I induced to the right. Once we open this switch. Okay, so remember, using Lenz's law, a decreasing magnetic field to the left creates an induced magnetic field to the left, which means that we have a current from right-hand rule that's going to go to the right when you're down here. Oops, when you're down here.
Four situations. And with this one, you can see this is like sort of a cross-section of a loop, so you want to know, is it going in here and out here, or in here and out here? So this one, clockwise, counterclockwise?
Counterclockwise.
Counterclockwise, okay? So our initial field points which way? Into the page? Initial field points out of the page, okay? What's happening to the flux? It's changing, yes. Is it getting bigger or smaller?
It's increasing.
Smaller, why?
Area is changing.
The area is changing, okay? So this area, as this thing moves this way, the area gets smaller, which means your flux is decreasing even though your magnetic field stays constant, okay? So since you have decreasing flux, your induced field points the same direction. It tries to keep the same magnetic field through that loop, which means it's out of the page, which means the current through the loop is counterclockwise. Okay? How about this? In or out?
In.
In. Okay? So this initial magnetic field points which way? Up. Alright? Is the flux through this loop going to be increasing or decreasing as you move into that field? It's going to be increasing because out here the field is weaker than when you move over here. So since this is an increasing flux, that means the induced magnetic field for the loop has to be opposing the change. So that means the induced magnetic field points the opposite direction, which means the current goes in here and out here. All right? Here we have the answer written over there, but this is a magnetic field that's out of the page and increasing, which means the induced magnetic field is into the page because it wants to counteract. You can see the area doesn't change, just the magnetic field, and that means our current is going to be clockwise. Here we have something decreasing and into the page. That means your induced field points into the page. This is also clockwise. Okay, so induced field here, clockwise, induced field here, clockwise. This one's counterclockwise, and this one is into the page here and out of the page here.
Is that still involved in the right-hand rule, or are we going to something different now? Like, is that
So
still
we
apply?
use Lenz's law to figure out which way the induced field's going to be, and then we use right-hand rule to get from there to the current. So we've just added another step to the right-hand rule. All right? Okay, clicker question. Please discuss. We'll go again.
Clockwise.
It's week 12. Okay. Better. So look, what's generating the magnetic field? The original one. Current. Okay. So in terms of the loop, where is the magnetic field? The initial one.
Yeah.
Into the page, because we use right-hand rule. Basically, we use right-hand rule twice here. So we see this wire has a magnetic field into the page through this loop. Is that magnetic field going to get bigger or smaller?
Smaller.
Smaller, because as the wire moves away, we know it drops off as an inverse. So mu naught I over 2 pi r. So as r gets bigger, the field through here gets smaller. Okay? Which means your flux through the loop is decreasing. Which means in order to oppose the decrease in flux, we have to induce a magnetic field in the same direction as the initial magnetic field, which means it's into the page, which means that your current is clockwise. Okay? All right. Just one more time. Hopefully, one of these we're gonna get 100%. I can just feel it. Very pretty. Very Gaussian. Okay. Seems like the discussion ended. Ooh, so close. All right. Fortunately for you guys, I'm out of these questions, so we're not going to do any more. But the answer is into the screen, okay? So as this thing moves this way, what's happening to your flux? It's decreasing, because even though the magnetic field is constant, what's changing?
Area.
Area. And so we know it's decreasing, so that means this induced current is giving you a magnetic field in the same direction as the original magnetic field, and if you use right-hand rule, that magnetic field is into the page.